Okay, thank you very much. So I'm going to discuss ETL for pharmaceutical manufacturing as a part of D-DAP project, Digital Design Accelerator Platform. We have started developing a D-DAP ETL tool, that is extract, transform, and load tool. For handling all the data problems that we are discussing today, that we don't have data, if we have data that is not in the machine readable format, we cannot use it directly. So to solve the problems, we have proposed this. So I'll be discussing the overall architecture of D-DAP ETL, how we are moving towards structured data, what type of data we are dealing these days for ETL, and our plans to extend it. How we are moving towards global data and the databases that we are developing for D-DAP, and the ontologies that we need for metadata handling and for making search, making data fair, searchable. So I'll be also discussing existing ontologies and the ontology that we are developing for a D-DAP project, and how we can use this for semantic search. So a lot of data we have seen in pharmaceutical domain coming from different instruments. So for our ETL, we are taking raw data from instruments. When we have seen the data, it is in different formats. Sometimes we get data in Excel sheets. Sometimes we have data in CSV formats, and other times we have data in text formats or out files. So people have spent a lot of time and they have spent a lot of money in producing that data, and that is very valuable data. So we are dealing with that, and we try to save that data for future use. So kind of data that we are discussing at the moment, dealing at the moment, is Brookfield powder flow, data from Brookfield, data from FT4 and GeoPic data. When we talk about ETL architecture, so the challenges that machine has to face, data is heterogeneous. It's not only heterogeneous at format level, it's also heterogeneous at syntactic and semantic level, because all people are not using same type of terms. They're using different type of terms. Semantically, they may be same, but actually, semantically they may be similar, but actually they are not, or there could be the other case. People might be using different terms to represent the data. So machines cannot understand it. This is another problem. There are no standards available. There is no common database from where we can quickly extract or grab the data and use it for further machine learning and artificial intelligence. And there is lack of semantic understanding. So to solve all the problem, we are trying to move towards the structured data by having ETL, so that we can easily extract the data, we can easily query the data, and can reuse it for further use. For all that, we need knowledge management, and for knowledge management, we also need ontologies that can help us in data management and data searching. So here you can see the overall architecture of D-DAP ETL process. This is actually in 3 parts: D-DAP extractor, transformer, and loader. With extractor part, a company or any customer, he or she can upload the file, the data file coming from the instrument. And from these files, our D-DAP extractor will clean the data. It will extract the data and convert it into local schema. For local schema, we are converting into XML format. After D-DAP extraction, we have to deal with different challenges. Data is not in the right format for the database. So we have to transform it. Different type of transformations we have to do, and for that we are developing ontologies for data transformation and metadata. And after transformation, once transformation is done, we can move the data to the database, and it will be saved there. And from database, the data visualizer tool that can be connected directly with the database tool, with the database, and it can extract the data, and you can do some artificial intelligence and run different algorithms on the structured data. Or for searching data, we have semantic search that is using ontologies at the back end. So I'm showing you some screenshots from the data that we are dealing with. Here you can see data. This is coming from Brookfield powder flow tester. So when companies or customers they deal with us, they say, okay, we need this part of data from this sheet or this part of data from this sheet. So what we have to do, we have to write different, you can say, parsers or extractors, part of D-DAP. And it can read the files and extract the data. Here, maybe his company is not interested in whole sheet. They are interested in temperature or humidity part, this part of the data. Here, they are interested in this part of data and the lower part. So you can see that sometimes data is available horizontally, sometimes it is available vertically. So we have to write parsers that can automatically extract and then further transform and load the data. So with D-DAP extractor, you can see this data that I have shown you before has been converted into XML format. This is coming from Brookfield shear cell related to flow function. So this is wall friction data coming from Brookfield shear cell, again another Excel sheet. Sometimes data is available vertically. Okay, here we are interested in lowest in density and the highest density part, maybe. And here we are interested in different parts of the sheet. So at the back end, we have to work on extractors that can extract the data. And here you can see our extractor loading data, converting data into local schema format, that is XML. Now you can see this is another format. The last one I showed you, it was Excel sheet. So now this one is out format, text, a kind of text format. This is data coming from GeoPic, from Pfizer. And here they are interested to have this data in the database and want to do some further stuff with it. So our extractor converting data into XML format. Here this is another data coming from FT4. In this sheet, we can see that data is not in one file, but it is in multiple worksheets inside the sheet. So we have to go to different sheets, grab the data, and then further we need to transform it. Another FT4 data coming related to compressibility. SVFR data coming from FT4. Okay, so this one is data. This data is coming from ring shear tester related to wall friction. Again, this is in text format, and we are using different APIs for converting the data into text format, into XML format. So for Excel files, we have Apache Poet jar that is a driver that is available for converting and loading the data, further transforming the data. So this way, we can add more and more instruments, and we can further transform the data and move towards the global or standard schema. Here you can see the D-DAP data schema based on current data coming from partners related to wall friction and flow function. This schema actually provides the configuration for our D-DAP database. This is related to wall friction and flow friction and flow function. And here you can see the details of those global schema from wall friction. This is coming from flow function. So now we are working on extending our database so that we can have more and more instruments. Now, why we need ontologies here and where we will be using ontologies. So those who are not aware of ontologies, so I just want to give a little bit introduction of that. So whenever we have ambiguity of terms in the files, or when we want to search the data, so it is possible that everyone is not using the same term for searching the data. It's quite possible that one is using a term lactose, find me the data for lactose in the file, or another might be using milk sugar, and same way there are multiple names for different instruments. So we are developing ontologies to resolve the problem of ambiguity of terms. So these ontologies are actually proving as a backbone of knowledge management processes. So not only this problem, this will also help us in developing standards and to clarify the domain structure knowledge, and it also help us in knowledge sharing. When in future we are extending our semantic search, and so we need to work a lot on extending these ontologies for pharmaceutical manufacturing domain. And other applications that are working in information extraction and integration. Suppose if you are working on a project where you want to extract information about assays and drug products or materials or test methods, and you're doing NLP, so these ontologies can be reused over there as well. So these ontologies can help us in not only in information retrieval but also in information integration, and also in translation. We can also do some reasoning with ontologies. If we make our data fair, so our data will not only be machine readable, it will also be a machine interoperable. It means like we can not only read it, but we can also connect it and make our data linkable. It can be linked to further ontologies and can be linked to further ontologies and systems, and can infer more information from the existing data. So for D-DAP related ontologies in the drug manufacturing domain, we have investigated existing ontologies so that we can reuse few ontologies, and then we can extend further for D-DAP project. So we have seen ontologies from Purdue University that is dealing with some drug manufacturing terminologies. Ontology from Campbell, and there is one from BA4, that is basic formal ontology. There is one from Allotrip Foundation in the field of chemistry for process chemistry. For national drug files, there is NDF-RT ontology. These ontologies are publicly available. We can easily reuse and integrate them in our applications and resolve the problem of ambiguity of terms. We have drug ontology, DRON, and but the problem is in these existing ontologies, we don't have much information about pharmaceutical manufacturing. Like we don't have assays, we don't have test techniques, and these types of things, the terminology related to these. So we have to extend these or integrate these, merge these ontologies with our application, so that we can further make it, can apply to semantic search as well. For developing ontologies, we have a web ontology language, and the tools that we are using are Protege. We are also using web Protege if we have to collaborate with other partners. For extracting data from ontologies, we are using Sparkle, that is a simple protocol and RDF query language, and the framework that we can use to collaborate with Sparkle endpoint is RDF4J. So these tools and techniques we need for D-DAP ontologies and project. Here you can see a few screenshots from our existing ontology. We have just started it, so we have to extend it. So here you can see it's these are classes and information about materials, about excipients, about excipient roles, about assays. We have information about test methods and unit operations. So we can, what we can do this way, you can see here that we can link our information, our experiment, with different assays, with the test methods, test techniques. Here you can see the CABI ontology coming, this is chemical entities ontologies with more than 170,000 classes. And for material names, we are reusing it. We can link it with our ETL. And here you can see that we have a lot of synonyms and extra information that we can link with our existing databases and extend the information. Here you can see the Sparkle query that we are running and extracting information from this existing CABI ontology so that we can successfully reuse it. Here you can see the information is, we are extracting information about lactose, but it is also extracting information about beta lactose or alpha lactose, the relevant classes. The few screenshots from the existing ontology from GraphDB. Okay, here you can see some information about tribasic calcium phosphate from the CABI ontology. So we can link these smiles, these labels, and these synonyms with our applications. So if somebody is extracting information with one term, but a database has not that term, then we can consult our ontology and can grab the information related to that term. Here you can see if user has given a query for xanthos, then it can extract the information about calcium phosphate or tribasic calcium phosphate as well, because it is linked with the ontology by using Sparkle and RDF4J. Few more queries. We can do search by mass, by smiles. So we are extending it by equipment synonyms. We are also developing a web interface where you can upload the file. It will be stored on the server. You can later download the file as well. Then your data will be available in XML format. You can also grab it in XML format, and your data will be stored in the database in the structured format. So if you want to process that data, you can grab each piece of information from the database as well. And then we can link the data virtually with the GraphDB so that we can convert our data into RDF format as well. So that is actually fair data. So we can actually then link it with further applications. So here you can see this is the web interface. Here you can see more in more details. You can choose a company, or you can choose the instrument type you want to upload. You want to choose the experiment type, the test type. You can choose a file, and just with 1 or 2 clicks, you can upload your data directly on the database. Yeah, this is one of the screenshot coming from GraphDB, where data has been uploaded and linked with virtualization. So there are different experiments. Now these are the experiment details. This was coming from flow function, Brookfield flow function. So here you can see the details that I showed you before. This is available. Now you have all slopes and intercepts. If somebody wants to do some reasoning on the data and want to predict the powder behavior, maybe, then they can extend. They can extract the information in RDF, and then further we can do some reasoning on that and predict the powder behavior as well. So these types of things can be done if we have data in RDF format. So this is coming from one experiment. So we can download it. Yeah, so same way we can add, and we are looking forward to add more experiments so that we can further connect this data to for artificial intelligence. This can help the domain experts to reap the benefits of digital age, and people who are doing the efforts on data visualization, they can directly connect to the data and visualize it. They don't have to spend a lot of time on data cleaning, data loading, and data for working with the data. So yeah, we have to further extend this ontology for drug manufacturing, and we will continuously working on that. So this work will actually help us to resolve the problem of semantic heterogeneity, the scattered data, and it will provide us the future foundation for future analytics, and can help the data-driven projects across the sector. And different people from data mining domain, from statistical analysis domain, from predictive analysis domain, they can connect with this and can gain the benefit of it. Thank you. If you have any questions, please. Yeah.
This talk, I'm gonna divide it into two sections. It's a bit longer than the previous ones because it was intended to be two talks, but in the end we decided to go for one, but it's a bit extended one. So the first part, we're going to talk about the project itself, the project that we developed, the applications, how they are, the experiment that we developed to test how efficient the applications we developed are. And then we're going to have a small pause where I'm going to show you a couple of videos of the actual outcome, the actual applications running. And finally, I'm going to have the second part of the talk where I'm going to talk about the implementation, the data capture, how we are able to create these photorealistic 3D models that we can use in many projects, not just the one that we develop here, but also many others that make use of lab equipment and what we can use also in developing like digital twin applications that make use of this model, and also how I implemented this using the video game engine Unity 3D. So a little bit of background, this project is part of the Articular project, part of the initiative, the CMAC initiative, and the development team is formed by people from the Glasgow School of Art, the School of Simulation and Visualization, and also people from the University of Strathclyde. So the introduction, I'm going to talk a little bit about what we developed in this specific project. Our objective was to measure how effective virtual reality is as a technology to develop applications to train people using different lab equipment. So after a few meetings, we decided that this use case was going to be focused around the CMAC workstation, chemical stirrer, and to measure how effective this virtual reality technology is, we decided to compare this against two other training methods. Tablet PC application in Android, and also a video tutorial. So a video tutorial that someone can watch in any video player. Also, we decided to do this for the task that we decided to do focus around the CMAC was the assembly and the disassembly. So people who are gonna run an experiment using this device are often, they need to disassemble it first, cleaning the pieces, assemble it, make the preparations, and then assemble it back again to start measuring and make whatever tasks they need. And if someone never tried, never used this device before, it's very important that they are familiar with it. This is a device that is usually booked, so if someone never tried it before, it might be very useful for them to try it out in virtual reality maybe. Also, if someone which is a novice, never used this before, they might make a mistake when they are assembling, they might break it. This is a very, very expensive device, so looking for alternative ways than using an actual device to training people was a very interesting project indeed to take to take place here. So I'm going to first talk about the virtual reality training, which is the main piece of development that we did. The application is developed using devices that are available for the public, that are available commercially. The VR headset Valve Index, and is also compatible with the VR headset HTC Vive. We decided to develop the VR application mimicking the different steps that the assembly and disassembly requires. We also find out that we have to, let's say, indicate what to do next. So if someone comes in and decided to start this from the start and there's no one around, how is the application going to tell them what to do next? So we provide a text console that explains what's going on, what to do next. There's also audio that there's a voiceover that explaining what's going on, what to do next, and also the next piece that needs to be interacted is going to start blinking after a little bit to indicate, yes, this is the piece that you need to grab. So after that, we also needed to study what are the best ways to interact with these elements. The HTC Vive and the Index have the advantage that the hands and the head are tracked. So when you're moving around the environment, it's very natural. It helps you familiarize with the environment, and the fact that you can look around and interact with these things directly is indeed a very a great advantage of the technology. So once we have the VR developed, the VR training developed, we have also to develop the tablet PC and the video tutorial. Now, the fact that these are three different technologies, three different media, we have to understand, okay, there are limitations to each technology, but the steps needs to be exactly the same. So each one of these trainings have exactly the same training reproduce. The tablet PC training was developed for the Samsung Galaxy Tab 7. As this is the device we decided to go for, but thanks that we are using a multi-platform video game engine, potentially this project can be exported to iOS as well, and although it's not tailored to smartphones, this application will run easily on any Android devices, or if exported to any iPhone devices too. Just as the VR simulation, you can navigate through the different tags very smoothly. You don't have to click a button or anything. Once you finish a task, you go to the next one, and there is text, and there is audio. There is also highlights on the different pieces that need to be interacted with, and making things a bit more intuitive, let's say. Finally, maybe the less interactive method. We came here to the University of Strathclyde, where they have an actual real CMAC device, and we recorded the whole process to develop a tutorial. We also use the same voiceover for the video. We recorded a specific voiceover for the video, but it's the same person making the voice. We are using the same kind of guidance step by step, and the length of the tutorial is very similar to the VR and the tablet PC tasks, applications. So once we have implemented everything and it's ready, we need to know how effective these applications is. Is it actually useful? Do they work? And to do that, we have completed 2 phases so far. We developed a pilot study here at the University of Strathclyde the 19th of January, where 9 participants tried the applications, give us valuable feedback, and basically demonstrated that what the actual application and the whole process does work before going to the first trial, where 13 volunteers went through the whole process and tried all of the training applications and performed the actual task with the real ECMAX. I'm going to explain what methodology we use right now, but we are also expecting to do another trial in the next few months to gather more data. The methodology. So how can we decide if this application is effective or not? How can we know if this can be used for training people? We decided to divide all of the participants into 3 different groups. Each one of them is going to go for one of the 3 training methods, and they are going to go through the actual task with the real ECMAX. Before they start the training, we need to gather some background data from them. The study is completely anonymous, but we need to know if the person knows about anything about the ECMAX. Maybe they have performed this task before. Are they familiarized with lab equipment? Are they familiarized with virtual reality? Maybe it's the first time using this technology. So after doing that, they will go through the training and the real assembly of the ECMAX at the lab, and then they have a chance to also try the other 2 training methods. During the real task at the lab, we do assess how efficient they are. So there is a supervisor analyzing how accurate they are doing the training. Are they able to complete each step? And then we can compare if this training has been effective or not. Finally, once they tried the last 2 training methods, we asked them their opinion and also feedback. It's very important for us to know, have they enjoyed the experience? Will they be willing to do it again? Will they recommend this to anybody else's? Is people open to go to try this technology that maybe they never tried before? So this is very useful for us to maybe do changes on the development. Is this actually ready to go? So because we only have 13 participants so far, we cannot get significant statistic data, but we can get we can have a look at the feedback that we have, and we can know if is it this being a successful application? Are the people enjoying it? So far they do recognize that the training they went through, so either VR, tablet PC, or video, it had a positive effect on them to do the actual task. So that's at least something that is good to know, that what you develop helped them out to do it. And then the one that they liked the most apparently was the virtual reality so far. So that's good to good to know at this point. The application that we develop is openly received by the people who tried it, and we have very positive feedback. Many people would love to have this at their university before actually go to the lab and try it out in real life. First, I'm gonna show the VR application. This application is available at the conference room number 6. So after this talk, if you decide to have a go at it, you can. As you can see, the advantage of using the valve index is that you can also track the finger, so you can actually grab things very naturally, aim and grab things very directly. We can imitate the motions that the hands do when they grab and then pull out things and move them around. You can also notice that the lab we created is quite realistic. We created this having the lab that we have here as a reference.
Open the clamp chain, touch it, and click the trigger.
So you can see a little bit of the audio there. So during the entire experience, there is a voiceover that is explaining what is going on, what to do next. And you can see each one of the steps. There is a whole flow going on here. The participants is doing the same thing that they will do in real life. In real life, they're not interacting with buttons, they're interacting with the actual device, and they can go to the next step. They are not stepping to look at a book or interacting with buttons. We try to do this very natural. So the tablet PC training has, of course, the limitation of this being in a tablet. You don't have the advantage of being immersed into the lab. But we can mimic the same procedures that have been done in the virtual reality training. Actually, we are using the same model. One of the great advantages of the 3D models we develop is they're highly optimized, and they can be used in VR, they can be used in mobile devices. You have to be careful when you develop photorealistic models. If they have too many polygons, they might perform badly on limited devices. A mobile device is not as high performance, as powerful as a VR PC. As you can see, everything is guided. The pieces blink. This is the next piece to do, and as the previous VR version, you go to the next step very organically. And you can see how in this step, for instance, we change the impeller over here. So over there, we change the impeller, and now I'm going to show you the same step on the video tutorial training. So over here, we have the real CMACs. We have the same task. We remove the probes. We change the impeller. We pour the chemicals. We assemble everything back again. I want to show you something about the VR that is very interesting. The fact that we have tracking fingers means that we can actually use our fingers to type in a real trackpad, in a touchpad, the same way we do it in the lab. So that's how we input data. It works exactly the same way that it does in real life. That's the first part of the talk. So we can now go to the second talk. After this, there will be a session, a moment for questions. So, okay. So now I'm gonna talk more like maybe something that is more in the making of what was going on behind the scenes. How is it possible that we can create all of these models from nothing? There is you can see that the textures, the screens that we use are based exactly on the real EasyMax device. So there are basically two main parts for the implementation. One is the asset creation, so how we create the models. And then the second part is the implementation, how we add the features, how we implement this in virtual reality, how we implement this in Android or iOS. So for the modeling part, we use our modelers, our team of modelers used 3ds Max. And then for the implementation part, I use the video game engine Unity 3D. So first of all, how many stages? How can we create these 3D models? First of all, we need to gather the data. We need to know how big these elements are, we need to take measurements, how each one of the elements, how long it is, the diameter. We take photos, so we know the colors, the textures of each one of them. And we also interview people from the University of Strathclyde. We need to know how these pieces go together, how they work, and with that data, we can proceed and actually start blocking out the 3D models. Just with the photos and the measurements we took, it will be too hard to create exact replica. Thankfully, we can also access data from the manufacturer. So the actual manual from the CMAC have cut drawings that show the specific measures of each section. So that's really, really useful for our team of modelers. They can actually load these 2D data, these 2D CAD data into 3D Max and start creating the 3D model of it. This 3D model, of course, doesn't have any textures yet. Every data we have is really, really important in order to fill out the blanks. Some data might not be, some measurements might not be present on the manual. Some photos that we took might not fill out the entire data that we need. So how are we able to put everything together? It's basically gathering as much data as possible. So also, we like to mention here that the models that they created are tailored, are very optimized towards VR and mobile applications. They use this method called polygon modeling. This allows to create optimized models that run very efficiently. If this was not a restriction, for instance, if they were doing a 2D render, maybe a 3D video, like the 3D movies that you see, the 3D animations, they wouldn't have such a limitation. But here we have to be very careful how many polygons each one of these models have. This has to be rendered in real time, so that's really important. So once we have the model blocked out, it's time to create a texture so it looks so realistic, let's say. So it says we create the materials. So the materials in modeling are the assets that allows us to mimic, for instance, the reflections that the metal has, how the glass reflects, and then we add a texture that mimics the same colors, the same pattern that the real element has. And this has been done, of course, taking the different photos that we took. So thank you. After all of this, we can get like really, really realistic renders that if it's not because the real one is quite wear off, you couldn't tell which one is the real one. I will dare to say. But of course, these ones are for renders, not for real time. So, but we can still use these same models to create this data. Outside the models, we use 3D Max as well to create different animations. So, for instance, how all of these pieces getting together, how they move. For instance, we have the clamp chain that opens and closes. We use the 3D Max to create this animation to represent how it moves as well in real life. And then we have basically this is how we go from just a photo, from just a lot of photos, of course, at the beginning, to a photorealistic 3D model that we can use. In this project, we used it for a virtual reality training application for the CMAC, but it can be used for a number of different projects. For the environment, we also follow a similar procedure. Of course, here we have a bit more freedom since we can adjust the lab to our needs, so how big we want it, or the measures, we don't have to be exactly to the millimeter as we are with the actual CMAC. But you can tell that the 3D model is based on the real lab that we have here at Strathclyde. So outside from that, I would love to show you a few examples of 3D models that we have developed at the Glasgow School of Art. We have been working with Strathclyde in a few different projects, not just the CMAC. So our modelers, Sam Rice and Craig Logan, develop a number of models here. You can have, for instance, you can see, for instance, the twin screw extruder. Here you can see the MSMPR. You can see here the seed generation, the photo and the model, the filter dryer, and the dissolution tester. So once we have the model, we can load this into the Unity engine, into the video game engine Unity 3D, and we can start actually interact with this thing. We can grab the different parts, put them together. Basically, we have to implement the different features that we decided we need to do to perform the task that we have to do. As I mentioned before, the fact that we're using Unity 3D allows us to create from a video, from a virtual reality application for Windows 10, and also a tablet PC version of the project for Android. So it's very versatile. It's a great tool. So to finish, I would like to also mention other types of data capture that we use at the School of Simulation and Visualization. So and that is also quite interesting. Like when you go and decide to create a 3D model, how are you going to gather the data? How are you going to create the 3D model? So one of the options will be photogrammetry, which is a technology that allows you to stick together a series of photographs and create a 3D mesh of the object that you are creating. There are, of course, its pros and cons. This technology can be a bit challenging if you are creating models of reflective objects. For instance, if they have glass, if they have reflective metal. There are workarounds around that. Just for instance, we could use polarizing lenses. We can especially create a especially illuminated room, but for this specific case of lab equipment, we decided to go for the other option of using CAD data and photographies. Another data capture method will be laser scanning that uses laser scans to create point cloud data of the landmark, object, building, statue that you want to create in 3D. We decided not to use laser scans for the same reason that photogrammetry. It's a bit challenging to do laser scanning on reflective objects. The laser bounces differently when you are not doing on reflective, non-reflective surfaces. You could work around, of course, using like a special powder, and you can spread the reflective surface with that. But of course, doing that on very expensive lab equipment will not be a very wise decision. And then finally, we have maybe a compromise between photogrammetry and laser scanning, the structured light scanner, which is a handheld scanner that allows you to create 3D meshes of of smaller objects. And historically have suffered the same problems than the methods we had before, although the more expensive state-of-the-art ones are able to scan black and reflective surfaces much, much better. So when you decide to create a 3D model of any kind of object, you have to choose the best technology that is tailored to that specific use case. And of course, the other methods can be very, very effective when you are creating photorealistic models of certain objects. But you also have to have in mind that these create just one piece of a mesh. It's just one solid object. For this experiment, for this application, we are actually moving things apart, pulling things, putting them back. So we need to create this 3D version, and then we have to create smaller versions of the different elements that we have to move. So that's why we decided to model each individual piece individually the way we did. And that's my presentation, so I can take any questions now. Thank you.